Okay, so hello everyone. I'm very excited today to welcome one of our own. We have Namrata Vaswani here. So Namrata, she's the Anderlich Professor of Electrical and Computer Engineering at the Iowa State University, and she received a PhD from the University of Maryland in 2004. Her research interests lie in data science with a particular focus on statistical machine learning and signal processing. And at Iowa State, she also directs the Sci Math, which is a graduate student led K-8 mentoring program, math tutoring program. And Namrata has served as an associate editor, area editor, or guest editor for several journals such as IEEE Transactions on Information Theory, Transactions on Signal Processing, the Signal Processing Magazine, and Proceedings of the IEEE. She is also a recipient of the 2014 IEEE Signal Processing Best Paper Award and the UMD ECE Distinguished Alumni Award, the Iowa State Mid-Career Achievement in Research Award, and an IEEE Fellow in 20.
Hey, I lost you. Can people hear me?
Yes.
Okay, I lost Sangamitra, but should I just begin?
Let's ask somebody else. Can we all hear Namrata? Yeah. Okay.
Okay, so yeah, I think with that, and most recently, I think the reason why she was visiting DC is because she just got she just got this AAS fellow award. So we can have Namrata start the talk, I guess.
Okay, thanks Sangamitra for the nice introduction. And sorry I couldn't make it in person today. But hopefully people still have the patience to bear with Zoom. I'll make sure I'll keep it short. I'll give you the most important information in the first 10 minutes. So I'll tell you about an algorithm that we developed, which we call alternating gradient descent and minimization, and how it's both fast and communication efficient for certain types of problems. I should mention this is work that I started with my former graduate student, Dr. Sayede Sara Nair. And some of the MRI applications are being developed with my current grad student, Shilpa. The three papers based on which this talk is based are listed here. So here's a quick outline of the talk. I'll tell you the overall idea of AltGDmin, which is, if you understand alternating minimization, it's just one tweak to alternating minimization. Then I'll talk about the LR low rank column-wise matrix sensing problem, which is where it was developed, and it's one of the problems for which it is both extremely time efficient and communication efficient. Then I'll talk about two other problems where it is useful, either time-wise or communication cost-wise. Matrix completion, it's mostly its advantages in the communication cost, not in the time cost. And then the last, so item 3 and 4 will be short. So item 3 will be just 2 slides. I'll just briefly mention this. Item 4, I'll spend about 20 minutes on the application. The interesting thing about the algorithm is that with very simple changes, it also works really well in practice for actual real data undersampled dynamic MRI. And I'll explain what that means as we get there. Please feel free to interrupt me during the talk. I also have chat open, so if you want to message on chat, that's fine. I can answer it. Or Sangamitra, if you see a text on chat, please just stop me and ask the questions. My talks go much better if you ask questions in between rather than waiting till the end. Okay, so what is AltGDmin? So consider a general optimization problem. So Z is my unknown variables. Y is what I'm using to refer to the data which I have. So gradient descent as of today is the most common optimization solution because it's fast as against modification. But it needs at least almost everywhere differentiability. You cannot use it for discrete problems. And more importantly, even where problems are nice and continuous valued, it may converge slowly, need a small step size, or may not even converge at all. And then so for some classes of problems where gradient descent is either very slow, needs a very small step size, or does not converge at all, probably, people have designed a heuristic called alternating minimization, which is typically useful, which by useful I mean it converges quickly. First it converges, and second it converges geometrically. If my unknown variable z can be split into two pieces, I'll call them ZA and ZB, such that minimization with respect to ZA, keeping ZB fixed, and vice versa, are both either closed form, or otherwise you have a reliably correct algorithm to solve each of them individually, but you don't have a similar algorithm for the overall problem. The advantage of Altman is, in certain settings, it's fast convergence speed, which means low iteration complexity. But the disadvantage is the per iteration cost can be high because you're solving a full minimization over half the variables in each iteration, right? So, and this is typically the case if both or one of the two minimizations is expensive. I mean, doesn't have special structure. Now, for certain problems, what happens is that so if there is classes of problem in which minimization with respect to ZA is expensive, but that with respect to ZB is quick and fast, then you can use a simple tweak. You replace the slow minimization step by gradient descent. If one of the two minimizations is expensive, you replace that by a single gradient step. And this simple change is what we call RGDmin, but the simple change makes your algorithm much faster. And then typically the cheap minimization, so let's say ZA is the slow variable or the expensive variable, and ZB is the cheap variable. The other minimization is cheap usually because it can be decoupled. And when this decoupling holds, you can actually argue that a federated or a distributed implementation of RGDmin is also the most communication efficient compared to both gradient descent and Altman. Roughly speaking, for such problems, many such problems, which I'll talk about 3 in this talk, you can get a per iteration communication cost and time cost of gradient descent, but you can get an iteration complexity which is comparable to that of Altman. Okay, so here's the same idea in a little more detail. So you're splitting, so you have to minimize over Z. You're letting your Z be split into two pieces, ZA and ZB. It could be two different matrices, or one could be a discrete variable, other could be a real valued variable. Now decoupling with respect to ZB means that you consider the cost function over ZB. It decouples into, so it can be written as a sum of simpler cost functions, each of which depends only on a subset of ZB. So ZB could be a matrix, and ZBL is the Lth column of that matrix, for example. And also data-wise, there is decoupling. So ZBL depends on only a subset, let's say YL, one column of the data, for example, right? Or a subset of columns of the data. And ZBL could also be, instead of one column, it could be a subset of columns. For such problems, RGDmin you can argue that it's both fast and communication efficient if this property holds. And then if this property does hold, which we call partial decoupling, here's the algorithm. You initialize ZA, you alternate between updating ZB by minimization, keeping ZA fixed at its previous value, Z hat A, you're minimizing only ZB. Because of the decoupling, this minimization, you can solve for ZBL, which could be, so ZB could be a high dimensional matrix, but one column of it could be, so ZB could have one high dimension. So ZB could be, let's say, R cross Q, where R is small, but Q is large. So you're decoupling this into Q small minimization problems. each of which is quick to solve. And then you're updating ZA by just one gradient step at each iteration. So this is your overall iteration. You're alternating between a full minimization for ZB because it's quick, and a single gradient descent step for ZA, keeping ZB fixed at whatever previous value you got here. Okay, and eta is the step size. Does this make sense?
Hi, Namrata, this is Prakash. Hi, I have a question.
Yes.
Yeah, the function f you assume to be differentiable. Does it have any special properties with regard to ZA and ZB, which renders one optimization less difficult than the other?
Yeah, so it has the decoupling property, right? So this optimization with respect to ZB is depends on, so subsets of ZB depend on subs. So my cost function can be written as a sum of these cost functions here. Let me come to the next 3 slides. So I just gave a general algorithm just to, if people want to go to sleep after this talk, this is it, after this slide. But I'll come to the low rank column-wise sensing problem, which is most of this talk, where I'll show how this decoupling occurs.
The decoupling is enough to do the job, or do you have to make any additional assumptions?
The decoupling is enough to guarantee per iteration time and communication cost improvement. Now, of course, to prove that the algorithm really converges, you need to do more. And
That
how
was
many?
the question. Yeah. Okay. Very good. Thank you.
Yeah. There you need a lot more. So I'm just saying, at least you could consider implementing the algorithm and trying it out for problems where this kind of a decoupling occurs.
Thanks.
Okay. But there is a lot, I mean, the analysis, the sample complexity and what is called the iteration complexity, or some people call it convergence speed, that has to be done on a problem by problem basis. So we don't have a generic solution for all problems. But classes of problems where there's a lot of problems in low rank matrix recovery where this partial decoupling property holds. There's 2 problems I'll talk about in this talk. And then there's also partly discrete problems, which we haven't studied yet. We had a proposal. So like problems like clustering, alt-GDmin could potentially be a replacement for simple k-means clustering, or unlabeled sensing, where you again have the permutation matrix is a discrete matrix, so you cannot use gradient descent at all for such problems, but you can potentially try to use alt-GDmin. Here we haven't studied these yet. We don't have any even simulation experiments. Oh, sorry, I forgot to. Here. Yeah. And so here is 3 problems. So low rank matrix recovery. Sorry, excuse me. Yeah. Sorry. Here. So here in low rank matrix recovery, the goal is to recover an n cross q rank R matrix X star with columns X star 1 to X star q. So there's the matrix sensing problem, which is linear projections of the entire matrix X star. I think this problem was created just to write papers. There's not too many practical applications of this problem. There is the matrix completion problem, which has a lot of real life applications, where you want to recover X star from a subset of its entries. Of course, you need more assumptions, which we'll come to. This has key applications in recommender systems, the Netflix problem, for example, and a lot of video analysis. Now, of course, here you need an assumption because you have completely local measurements. You need rows and columns of X star to be dense in a certain sense. And this is ensured by the now well-known incoherence assumptions on the singular vectors. Now there is the 3rd problem, which is in between these 2 problems, which is called low-rank column-wise sensing, and then also phase retrieval, excuse me. This is the problem I'll talk about. Here you have column-wise linear projections of X star k. So for each column, you have a dense linear projection. AK could be a random Gaussian matrix for the sake of proving theorems, and AK is a partial Fourier matrix for the sake of, say, the MRI application. This is not as well. First thing, this problem wasn't as well studied at all until 2018, 2019, as completion and sensing, which have been extensively studied. Here you have, it's an asymmetric problem. So you have measurements that are global for each column, but across columns, they are non-global. And hence, all you need is, you need to assume incoherence of only the right singular vectors, okay? And this is the problem on which most of this talk is based. So here's the same problem in detail. So, so each column X star K, you think of, so if you look at the MRI applications, you want to recover a sequence of images from a sequence of MR measurements, which are essentially Fourier transform coefficients of the images. For the sake of understanding the problem, let's vectorize the images. So X star K is my kth image vectorized. N is the number of pixels in the image. AK would be for the sake of the application, it would be the partial Fourier matrix undersampled. So it'll M cross N, M smaller than N. And YK is my Fourier samples the MRI scan data that I obtained, sorry. This is, I think and then there is also the multitask linear representation learning problem for what's called few shot learning in MRI. Essentially, it's multilinear regression. So we learned about this rather recently, but it's the exact same problem, exact same mathematical problem, exact same solution approaches also that we found out about more recently from some ICML papers. And then when I say federated setting, here I'm saying column-wise federation. So disjoint subsets of YK are observed at different nodes. Okay, so that's the federated setting I'm assuming here. Here's my incoherence assumption. So consider the R SVD of X star as U star, sigma star, V star transpose. We'll refer to this as B star. So what I want is columns of B star have roughly the same energy in them, is my assumption. And said another way, I want each entry of my V star matrix to be dense, to be roughly of the same magnitude, right? And this is needed for correct interpolation across columns. And the way we ensure this is by ensuring that every row of V star, which is every column of V star transpose, has roughly a similar norm or a roughly similar energy. Okay. Again, this is the standard incoherence assumption from matrix completion literature, if you're aware of that. Okay. Now, why a new solution? Now here, the LRCS problem, the column-wise sensing problem, you're writing your X as U times B. So your cost function is, so U is my N cross R matrix. So you've imposed the low rank constraint indirectly by factorizing my X as U times me. So U is a very tall matrix, B is a very broad matrix, okay? And then your cost function, you're writing xk as U times bk, and this is what your cost function becomes. So, sorry. So Prakash, notice here, this is what I mean by decoupling. So notice in this cost function, my bk appears only in the kth term in the summation. So the optimization over bk can be very cheap. Whereas U appears in all the terms, U appears in all the terms of the summation. So minimization over U keeping B fixed will be expensive.
Okay, thank you.
Yeah, so Altman is expensive for that reason. There is existing gradient descent based solutions, which could be standard gradient descent over UB, which is referred to as factorized gradient descent. This has certain issues. The only way to make it work in past work is to consider a norm balancing term, because you're writing X as U times P, but you could also have U times Q inverse times B. And one of U or B could start increasing in norm while the other could keep decaying, and that could be a problem. So you don't optimize for the original cost function, you add a norm balancing term. Now, because of that, you get, coupling in the solution. The second type of gradient descent algorithm that is studied for low rank recovery problems is what's called projected gradient descent, which means you do gradient descent over the entire matrix X. First of all, this is extremely slow and communication inefficient. But the second problem is, even if we don't care about complexity, it's hard to analyze it because I'm not getting a tight column-wise bound on xk minus x star k, right? In short, both of these solutions don't work with reasonable sample complexity because my problem is column-wise decoupled, but my algorithms are not column-wise decoupled. Right? Problem is decoupled column-wise, but the algorithms are not decoupled column-wise. So my xk, so in projected GD and in factorized GD, which is GD, xk depends on all columns of x star, the matrix x star, which is a problem because that prevents me from getting a tight column-wise bound on the x minus x star k. Okay. Alt GD min says I will deal with both problems as follows. I'll come up with a careful spectral initialization for you. This is a simple modification of existing approaches. I'll come to it. And then I will alternate between minimization for B, which becomes cheap. BK, remember, is an R cross 1 vector. R is small. B is R cross Q. So this looks like an expensive problem, but when you decouple it, it's cheap and it's closed form because it's a least squares problem. Excuse me. And then for you, all you do is you do a gradient step followed by QR decomposition, which ensures this norm balancing property. So this is basically the algorithm. And then for initialization, you first consider the standard initialization, which is A transpose Y, A1 transpose Y1. So you create this matrix, which I called X init full, which is using standard approaches. You can argue that this has X. So essentially, you're coming up with a matrix whose expected value equals the true unknown X star, or is close to the true unknown X star in some sense. Now, if M and Q, so M is my number of samples per column, and Q is the total number of columns. So if M times Q is large enough, you can argue that the span of the top R circular vectors of this X init full should be a good estimate of the span of the columns of X star with high probability. Now, to ensure this, there is a problem. Your summands are heavy-tailed, so you need too many samples to ensure this. Or said another way, a few bad YKIs can bias your average a lot. And the fix for this comes from standard statistics literature. We came across it in a recent Candice Chen phase retrieval paper. The idea is to sum over only the not too large YKIs. Don't sum over all the YKIs, sum over. So you replace YK by YK trunk, where YK trunk is YK with entries larger than a certain magnitude, zeroed out. And which entries are zeroed out? You compute a threshold also dependent on the YKs. Now, I think I'll let this slide be here for you to look at it for a minute because I don't think I did a good job explaining this.
So if I'm understanding correctly, is this some kind of robustness that you're trying to do here?
Not really. So this is truncation. So I should say bad is a, so no, what's happening here is your summands, you have A is a Gaussian vector for the sake of YKI is a Gaussian scalar. So you have squares of Gaussians appearing. So these are called sub-exponential random variables. And now for these, your sub-exponential norm is too large. So you essentially, you need too many samples to show correct convergence. Okay. So your trunk, and I shouldn't say bad. They are still AKIs will still be Gaussian, but your summands are Gaussian squares, right? So that's what I mean by bad measurements. I'm not talking about outliers or anything like that yet.
Okay, I see. Thanks.
So again, this whole idea borrows from something that was done for a single column X in a paper by Candice and Chen. I think the algorithm was called truncated Wirtinger flow for standard phase retrieval. And we borrow the same idea to matrices and apply it to matrices. And okay, mathematically, what you're doing is you're going from sub-exponential random variables to sub-Gaussian random variables. So essentially going from exponential like random variables to Gaussian like random variables, which are much easier to bound using law of large number results. So here's your complete algorithm. The QR step is done just to orthonormalize U so that your U and B norm, so norm of U always remains 1, and then norm of B won't keep going up or down too much. What you can show for this is, so you're assuming this mu incoherence of right singular vectors, which is the incoherence assumption. You're setting, if you can set your step size as this, or actually anything below point with, you could use any constant that's smaller than 0.5 and the result goes through. You use a step size that, you use total number of iterations that grows logarithmically with 1 over epsilon. And if my sample complexity is essentially the larger of nr square and nr log epsilon, so essentially for gradient, for the initialization step, I need nr square samples. And for the iterations, I need only order nr samples. Then with high probability, I can argue that each column is recovered to epsilon accuracy. And the subspace distance between U star, which is my column span of X star, and U, which is my column span of the estimated matrix, is also bounded by epsilon. Okay. And the time complexity needed is MQN is linear time. So it's only R log epsilon times, linear time. Communication cost is only, NR is the least you need to transmit a gradient. The gradient is of size N cross R. So you just need exactly NR per iteration and log 1 over epsilon iterations total. And the sample complexity is this, right? So it's fast, communication efficient, and sample efficient. Here is a quick outline of the proof. What you're doing is you're bounding initialization using Vaden's sine theta theorem, and then bounding each term using the sub-Gaussian Hovding inequality. And then at iteration t, you're assuming error is at iteration, and the rest of the argument is an iterative argument. You at iteration t assume error is below a delta t less than 1 and small enough, and show that the next iteration, the error is a multiplicative constant times delta t. So you're showing exponential error decay. To do this, you're doing 2 steps. You're analyzing the update of B first, and then using that to analyze the update of U. Okay. To analyze the update of B, you're showing bounding the error between B and a rotated version of B star. So you cannot bound B minus B star. Okay. You instead need to bound B minus U transpose U star times B star. Okay. Because of how B is being updated. And then the update of U is where most of the work is. This step is fairly straightforward, and it was all similar things were also done in our older work where we studied alternating minimization for the same problem. The update of U is where all the work was. Roughly speaking, you're using linear algebra. You're using the fact that the minimum singular value of R plus is the same as the minimum singular value of U tilde plus, which is here. So roughly speaking, there's linear algebra, careful linear algebra to get the desired form of bounds, followed by use of sub-exponential Bernstein inequality. Here's my update of B in detail. This is my closed form for B. because of this closed form for B and because my AKs are random Gaussian matrices, I can bound B minus B star K using this. This is where the probabilistic argument is. Use this to also argue that BKs are incoherent, just like B star Ks are. So essentially, this is my high probability bound. Then the next 4 steps are, linear algebra. I bound B minus a rotated version of B star. And then I get a column-wise bound on X minus X star also. And finally, I lower bound sigma min of B and upper bound sigma max of B. For update of U, I am getting these expressions. The basic idea to use is the expected value of the gradient has a nice simple closed form. And then when you project this thingy orthogonal to U star, you actually get rid of the first term. You get rid of this term. That's one key idea in the analysis. And the rest is using Bernstein carefully, sub-exponential Bernstein carefully, followed by epsilon at argument. So here's the algebra for people that are intimate. This will make sense only if you're intimately familiar with, say, matrix completion proofs. I'll just hold the slide here for a minute and you can ask questions.
So I have a question about the expectation assumption in the previous slide, like slide 15. Yeah,
No,
so
it's not an assumption. It's you can show this.
okay, it's not an assumption, it always
No,
holds.
no. You're using this key fact that expected value is this.
Okay, I see.
Yeah, because the gradient itself, notice I glossed over that part, has a simple expression.
Yeah.
This can be written as a sum over K and a sum over I. You can get a sum over MQ terms. And you can compute the expected value of each term pretty easily.
Okay, and is this happening because the gradient is somehow nice and linear?
Yeah, absolutely. You cannot do it for every problem. No.
Okay.
Yeah. This nice expression is coming because the gradient is nice and not linear, but conditionally linear, whatever.
Okay. Thanks.
Yeah. So this kind of closed form guarantees where you also you can actually show you'll converge to the correct solution in the statistics or signal processing sense can only be obtained for in problem specific settings.
Thank you.
Well, with a few caveats, which I'll come to in a second. Other questions, if there's any? Okay, I will move on to here. So here's what, again, I'll reiterate what I said. The time per iteration is nearly linear, is R times linear, which is actually the best you can get for any low rank recovery problem. All gradient descent algorithms for all kinds of LR problems don't need an extra factor of R. And the essential idea org-daemon works really well here, or it actually was designed with this problem in mind, is that the minimization over B decouples column-wise. So it's actually as fast as one gradient computation. So the entire over U, right? The communication cost is as good as it can get. Privacy is ensured for free. Your raw data YK stays local. Your updates of BK also stay local. So each node, my node K cannot estimate the entire X. It can only estimate U. And then because you're using this instead of full gradient descent, you're using minimization for one variable and gradient descent for the other. Because of that use of minimization, you can actually show a lot faster error decay. And that's why your iteration complexity is almost like Altman. Yeah, estimates XK are decoupled given you. So my other two gradient descent algorithms, projected GD and factorized GD, the estimates were not decoupled given you. Here's a comparison with existing work. There was a convex relaxation solution introduced by Justin Romberg's group in NeurIPS 2019, which had very high sample cost and very high time cost. By now, I think we all understand that convex relaxations are very slow. Then we studied alternating minimization. We actually studied it for the more general, the phase retrieval problem, but it trivially applies to the special case of column-wise sensing, linear column-wise sensing. Sample complexity is fine here, but time complexity here, because you're doing a full minimization over you have a log square term, which in practice becomes quite slow. And same, you have an extra log term in each iteration in the communication cost too. Gradient descent for u comma b, which is called factorized gradient descent, you cannot even analyze it for reasons I explained. If suppose we could analyze it, we can always implement the algorithm. The time per iteration, and if I try to extend results for matrix completion, it needs a very small step size. Even for matrix completion, where you can analyze factorized GD, it needs a step size that grows as 1 over r, because of which you get an extra r square in the time complexity. Projected GD is very slow and very communication inefficient, and you can't even analyze. And then RGD min has the best sample complexity, best time complexity, and communication cost for this particular problem, not for all problems.
Hi, Namrata.
Yeah.
In these comparisons,
Yes.
are there converse bounds which say that some of these things cannot be beaten, or it's still open?
No, there are not converse bounds. Yeah, people have tried. No. So no, I'm not aware of converse bounds. So in terms of sample complexity, you could go get down to NR, which would be the best. Then it's a trivial converse bound, degrees of freedom argument.
Mm-hmm.
But NR square, it's R times worse. In terms of time cost, I guess you cannot go below linear time, because that's the time you need to even just load the data.
Sure.
So in that sense, yeah, linear time is the best you can get, and then your R log epsilon times worse.
Mm-hmm.
Actually, same for sample cost. NR is so to recover something, you need to have at least as many measurements as the number of unknowns. So NR is the bare minimum you can go, and then you're this much times worse.
I see.
So,
all right, thank you.
yeah. Now, coming back to Sangamitra's question. So yes, you can do this. You can do this for either linear problems or almost linear problems. The phase retrieval problem is almost, it has an element-wise simple nonlinearity. So you're measuring each element-wise magnitudes of yk in the phase retrieval problem. There you can do a simple modification. You can recover bk instead of recovering it by least squares estimation. You're now solving an r-dimensional, a cheap phase retrieval problem, which is well studied in the literature. In gradient descent, you're replacing your y by y hat, which is an estimate of the linear y. And what was I going to say? The guarantees you need are R times worse. So sample complexity guarantees R times worse. But here too, you can analyze the problem, because you get one extra error term which needs to be analyzed, but it can be. And then we can also, matrix completion is again another linear problem with different properties. You're trying to recover extra from a subset of its entries. So here the algorithm is pretty much the same as for LRCS. Initialization is different. You compute the top R singular vectors of this Y matrix, followed by row norm clipping step, which is needed for ensuring incoherence. The guarantees are similar. And in this case, the only advantage of RGD-min is communication cost. Time-wise, alt-min is actually the fastest, because here my problem is decoupled. Matrix completion is decoupled both for U and for B. So You can't, in a centralized setting, you can't do better than Altman. A little more about matrix abletion. Algorithm is the same, guarantee is almost the same. You need slightly more samples because you have row and column wise local measurements. The differences in the proof are, well, one, you use matrix once time, but the extra work that you also need is to show incoherence of U at each iteration, okay, which takes a fair bit of work. In terms of comparisons, you can only talk about communication complexity improvement. And the reason it has the best communication complexity here also is because you're getting the per iteration communication cost of gradient descent, but the iteration complexity of Altman. Okay, questions so far?
So one naive question, but like, what do you lose, or where the other algorithms not suboptimal and we improve on all fronts?
Sorry? Here,
Yeah. So
here
here,
you mean?
do you lose anything by doing all GD, or everything improves? Like,
For this particular problem, everything improves.
okay, thanks.
Depends. Okay, I've glossed over the dependence on kappa, which is the condition number. Actually, the dependence on kappa becomes slightly worse in the sample complexity. But most literature, when they do algorithm comparisons, they treat kappa as a numerical constant. The other the other trade-off is in terms of practical. So if you have a gradient descent algorithm, you have a step-sized design. If you have an Altman algorithm, you have nothing to design. So that's a feature for practical usage.
Okay, thanks.
Okay, and then the other useful, so we looked at, so I actually at Maryland, my PhD was image processing and computer vision. So I've always looked at imaging applications for a lot of my work. Here, we looked at MRI as just a side application initially, but it turned out the algorithm worked extremely well. And then this became a PhD project in and of itself. Using the algorithm I just talked about for LR column-wise sensing for the MRI application. So my last 15 minutes is the MRI application. I'll just tell you. So in MRI, let's say Z star is my unknown matrix, unknown image sequence. Each column is one image. AK can be, as HK times F, where HK is my row selection matrix, F is the N cross N 2D DFT matrix. Your image sequence is actually a tensor of size nx cross ny cross q, but you flatten it into an n cross q matrix. Z star k is my, and then here, instead of just the low rank model, you kind of use what's called a 3-level hierarchical low rank model. You assume Z star k can be written as a sum of a mean image, which doesn't change across time k. Reason for this is MR images change very little over time. So there is a mean component if you subtract it out, the rest of the recovery can be much more accurate. There is the low rank component X star K, low rank matrix. And then there is extra modeling error. Of course, no model is perfect. So there is modeling error in this model. But by attempting to also estimate this modeling error, you actually deal with the high temporal frequency components, which you would want to recover in dynamic MRI. So this was the very simplified setting. Actually, what we worked with was multi-coil dynamic MRI, which is the standard type of MRI that's used these days. I'll skip these details. The modifications we made for MRI was we introduced 2 extra steps, one before RGDimen and one after RGDimen. The before step was, I said, I have a mean image that I want to subtract out before I do any low rank modeling. So I'll solve this joint optimization problem. recover my z bar hat, compute the residual y tilde k, which is y minus a times the z bar hat subtracted out, and use this as an input to the Orgy-Demon algorithm. Denote its output by x hat, subtract this out too, and then run a few iterations of gradient, call element of image-wise gradient descent to recover my modeling error E. This improves image quality quite a bit. And in MRI, mean squared error is not necessarily the correct metric. And then you output the sum of these three components. And we call this Orgy-Demon MRI. Because of course, I should mention here, my image sequences are never exactly low rank here. It's only a low rank is just a modeling assumption. So you want to recover the modeling error, or we call it a model error correction step. And then for our experiments, we did something which is not so common in MRI, but is needed if you want the algorithm on your MR scanner, for instance. You want to be able to compare across different applications and different sampling schemes, all with the same set of algorithm parameters. We looked at 4 different applications. And then also visually, so we looked at what's called retrospectively sampled MRI data, which is you had full sample data, but you undersampled it for the sake of comparison. Here you can get quantitative mean squared error comparison. And then we also looked at real scanner data set where you don't have any fully sampled images to compare against. So you can only visually evaluate things. But there are standard visual approaches, which I'll talk about. So here's a lot of the evaluations on retrospective data. My error format is error, which is the root mean squared error. And in parentheses, I have the time taken, reconstruction time. And then the last row, I'm just averaging all the 20 rows just to report one number and argue that, the 2 Orgy-Demon MRI versions have both smaller error on average and are faster on average. And then we compare with state-of-the-art L plus S low rank and low rank plus sparse algorithms from literature. And visually also we show the same thing this is for vocal tract imaging while speaking. This is retrospective Cartesian, cardiac perfusion and cardiac sign imaging with Cartesian sampling. So in row 1, we are showing one fully sampled image, which is my true image, if you may. And in the row 2, I'm showing what's called a time profile image. So it's one row of pixels across time. And that's called a time profile image. And if it's not clear, I can, if there are people that are interested in this, I can go over it in detail. But of course, as with all experimental results, what I'm showing is that our algorithm is competitive. Yeah. Okay. And this basically brings me to the end of my talk. So there's ongoing work. We've looked at Byzantine resilience in a recent ICML paper. The same problem, like I said, low rank column-wise sensing can also be called few shot learning or representation learning for few shot learning. Once you use the correct terms, papers make it to ICML more easily. If you call it LRCS, our original LRCS paper was also submitted to ICML, but did not make it. We are looking at Byzantine resilience for matrix completion. We're looking at Orgy-Demon for the robust PCA problem, which is the L plus S problem. These are some of the ongoing and future directions in this area. And that's it. That's the end of my talk. So here's a review of Orgy-Demon algorithm. And
it was very interesting, Namrata. I was wondering, did you happen to deal with problems with positivity constraints. I don't know, like low rank matrix factorizations where you have the extra positivity constraint or other problems like that. And did you
Actually,
ever?
I haven't. I haven't looked at them, but I'd love to. Yeah,
I,
that would
it
be
might,
an
it might,
interesting
it
extension.
might be very interesting. I mean, because some of them have difficult when you decouple, when you divide the Z into two subsets. Some of them have difficult minimization problems that you can maybe deal with your gradient descent method. So I was curious. Maybe you you can look at them and then we learn something new that might be very interesting. Yeah. So
Okay, sure.
very
So yeah,
interesting. Very
yeah, I'd
nice.
love to talk to you offline. So I am doing some Zoom meetings later in the day or tomorrow. So I'd love to
Okay. Okay.
talk with you.
Very good. We can arrange that. I'll ask for your contact and I send you mail.
Yeah, my contact is just my first name, Namrata at IE State. If you want
Okay,
to.
very good then. Excellent.
Yeah.
Nice.
Uh,
Are there any other questions? And I'm also sharing the speaker email in the threads in case anyone else wants to reach out to Namrata.
Ah, nice.
Thank you.
Thank you.
Oh,
So I have another question, like if we start to move away from like linearity and make the problem more difficult, like for instance, like add additional complexities, like maybe try to do something non-linear,
mhm.
what kinds of assumptions or steps would we need? Like would the Lipschitz assumption or some kind of local linearity, anything like that would help? Because typically, I mean, in some of the other analysis, it's like just a loss function, and then the loss function is maybe convex, or I mean, you talked about
Yes.
convexity, but strongly convex or Lipschitz. But yeah, people don't look at the actual form of the gradient, which you're able to do here and get guarantees. But if we were to think of a
Y-
general problem, what would be the
y-
difficulty?
Yes. So yeah, I've not found a student. I've not had the ability. I've not. Yeah, I wanted to work on this, and yes, I've thought about this in the context of proposals I wrote. So yeah, the general assumption you would need would be going back to my first slide. Uh, so what you would potentially need is for the minimization step to be fast, you'll need this kind of a decoupling property.
Okay.
Uh, and then for the gradient step, you're just doing gradient with respect to ZA. So for the gradient analysis, you may need partial. So if the problem is, let's say, what's called locally strongly convex with respect to ZA. And yeah, if it's locally strongly convex with respect to ZA, with respect to ZBA, suppose, let's keep it simple. Let's keep it linear and least squares.
Okay.
For starters, that's how you would
Yeah,
start.
yeah.
And yes, I had top level thoughts on this, but I haven't had the time to work on it yet. But I would love to. Is that what you're doing now these days? Are you into
So I
gradient
was
descent
interested
plus
into
plus?
the mathematics of this
Yeah.
optimization generally, but also I think another
Yeah.
thing I was thinking from your talk is some kind of fairness issues, like because the ZBs are different in different, you also talked about privacy, but if the ZBs are different across different,
Mm-hmm.
so each ZB is being optimized separately. If some ZBs have a good optimization and some ZBs have a
Bad
bad
optimization.
optimization or less data available.
Yes, and that would be a problem. Here you're assuming you have the same number of samples M per column.
Mm.
But yes, one could talk about. I haven't actually. Fairness is something I've not really looked into at all. But I know you. Have you? No.
Yeah, I'm working on fairness and
Yes.
explainability and trust.
Yeah, when we should. I mean, I'd love to talk offline.
Yeah, very happy to chat with you.
Yeah.